Welcome back everyone. In this lecture we will actually start with axiom of choice, and then later we will actually define what is called partition of a given set. So, let us start. So, we have this following important question about Cartesian products. So, we have seen that given two sets A comma B, let us say non-empty sets, using ZF axioms, using only ZF axioms, we were able to actually define what is called this A cross B. Okay. You can take it as exercise and then prove that ZF axioms are good enough to say A intersection B exists and A difference B exists if B is subset of A. Okay. Define these using only ZF axioms. Okay. So, the way we did it, so we wanted this ordered tuple A comma B, and then we realized them as this set which consisting of singleton A and the two set A B. Okay. So, then using this one could actually define Cartesian product of finitely many sets, and we need inductive hypothesis for that, mathematical induction, and that we will discuss later in this course. But anyway, using mathematical induction one can talk about Cartesian products of any finitely many number of sets. But then this actually kind of leads to a question that can we talk about Cartesian product of arbitrary family of sets. Okay. Let us say I am giving you a collection of sets. So, they are not necessarily finite collection. Okay. So, then like can you actually construct what is called Cartesian product of that. Okay. The Cartesian product that we understand when we talk about two given sets, and we also talk about Cartesian product of finitely many number of sets. But what is the meaning of Cartesian product of infinitely many family? Okay, for that let us try to understand what happens to the finite first of all. So, the A cross B is given by the tuple A comma B such that A is in capital A and B is in capital B. So, here we are making choice, like we take element from A and then we take another element from B and then we make this tuple A comma B. But then if you have infinite collection, okay, not necessarily finite, then how do you make this choice of picking an element from okay, each and every set? Okay, this seems to be like so you may convince yourself that what is the problem? You just, we know that they are all given to be non-empty sets, you just pick one and then you will be able to construct tuple. Na? So, what is the big deal about it? If you think about it, it is really a big deal, it is not that easy. For example, if I give you actually infinite family of pairs of shoes, then what you can do, you can actually pick one shoe from given pair. For example, I can pick just right shoe. Okay. There is a right leg and then shoe and then left leg shoe. What I can do, I can like each pair will consisting of two of them, right and leg. So, you just pick all the right leg shoes, then you will have definitely some collection. Okay. What if I give you identical pair of socks? Okay. I am giving you infinite many family of socks, all of them look, let us say look identical, looks like black. Okay. Then how am I going to pick my infinite collection? So, then there is this ambiguity. So, there is no guarantee that I will be able to pick. Na? So, when I give you socks, then when I give you shoes, then there are ways to do. You pick right or you pick left, that will give you the collection. But if I give you infinitely many pair of socks, then there is no definite way of picking a sock, and that leads to kind of confusion, and it also kind of leads to a following non-rigorous question. So, given arbitrary collection of non-empty sets, so is there a way to choose an element from each set? Okay. There should be a natural choice that you need to make. Who guarantees that natural choice? Apparently, that choice cannot be guaranteed by ejective axioms. Okay. So, we have to kind of impose that, so that we include that axiom of choice, and then we make this full list of axioms that defines the set theory. Indeed, the Fields medalist Paul Joseph Cohen proved that the axiom of choice is independent of the other ejective axioms. What is the meaning of that? That means the axiom of choice, it can neither be proved or disproved using the other axioms that actually we have in ejective axioms. Okay. So, that means you can think this axiom of choice as, even though it is natural axioms to include, it cannot come from the other axioms. So, we have to include it to complete the list of axioms. So, that is what we are going to do. But before that, let us actually try to understand what is this axiom of choice going to tell us. It is going to tell us about picking naturally some elements from given non-empty collection of elements. But what is the meaning of picking an element? Okay, if you think about it, the best way to actually phrase that, we use function language. Okay, let us try to understand first of all A cross B, then we will be able to understand the infinite analog of that. So, A cross B, if you think about it, so it consisting of the tuples A comma B coming from this A cross A in A and B in B. So, that means I am just picking the first element from A and the second element in B. Now, if you think about it, is there any nice way to write this? Of course, we used this set language to write the same thing, but that is kind of going to backfire us if you go to even like 3 or 4 collection of sets. It is going to get much more complicated. But then can we use some other language in order to write this? If you think about it, yes, what we can do. So, we are always saying that you are making the first choice to be an element of capital A and the second choice to be an element of capital B. So, the best way to record, you call that as a function. So, it is a function from 1 comma 2 to this A union B, where f of 1 belongs to A and then f of 2 belongs to B. So, I can actually write it as a function instead of, so the A comma B tuple corresponds to a function from 1 comma 2 to A union B, such that f of 1 belongs to A and f of 2 belongs to B. And this way of writing can be generalized easily to any collection, there is no question. For example, if I take A1 cross etcetera cross AN, then the typical element here will look like A1 etcetera AN. So, with this what I can do, I can define this function, which is a function from 1 to n to this union of ai, I range from 1 to n, where f of I just belongs to ai for all I between 1 to n. Okay. What is that f of I? That f of I is just ai. So, this way you can actually think this tuple as a function from 1 to n to this union of ai satisfying some property. Now, if you think about it, I can do this for any collection of sets. For example, if you have a collection, call it xi, which is indexed over capital I, where we assume that each xi is non-empty for all I in I. Okay. So, then what we can tell? We can tell that the axiom of choice is guarantees that there exists a function. So, this is what axiom of choice tells. The axiom of choice tells that there exists a function f from I to union of xi I in I such that f of I belongs to xi. So, what we are doing? So, since xi is non-empty, so you make a choice from each xi. So, you pick an element f of I from xi and then you form a function from I to union of xi, and this function is guaranteed using axiom of choice. So, the existence of such a function cannot be proved, and it can either be proved or disproved, not disproved using the axiom ZF axioms. Okay. So, if you include ZF axioms and this axiom of choice, you call it as ZFC axioms, which is ZF axioms plus the axiom of choice. Okay. Of course, in practice the axiom of choice is equivalent to many different interesting axioms. For example, there is Jones lemma which can be proved using the axiom of choice, that is what we are calling it as Jones lemma, and well ordering property, existence of basis, even existence of maximal ideals. So, there are plenty of statements that you can make, those are all equivalent to axiom of choice. Okay. So, at least we will prove some of them in this course, but I hope it is clear that what axiom of choice tells. So, if you have a collection of non-empty sets, then it guarantees that you can make a choice from each set. That means, you have a function from I to that indexing set I to the union of xi such that f of xi belongs to this A I. In other words, okay, you can write it as follows. So, you can define this what is called the Cartesian product of xi I in I, and basically axiom of choice tells you that this is non-empty. So, what is this? So, now I can't use the tuple notation, of course, one can also use the tuple notation. So, better to use this functions notations, that it is collection of functions such that f is from I to the union of xi I in I such that f of I belongs to xi for each I in I. Okay. So, now it is not very difficult to see this is indeed a set, because we are talking about collection of functions from I to the union of xi. The union of xi is again a set, because xi's are given to be a collection of sets, the union always a set using ZF axiom. Now, I is given to be a set. So, the set of functions from given set A to B, which is denoted by B power A, we already proved it is a set. So, since this is a set, so this is indeed subset of this union of xi power I. So, this is a set. So, now inside that we are collecting certain elements satisfying some property. So, that means using ZF axiom this is also a set. So, that proves this product xi I in I is indeed a set. But what is the axiom of choice guarantees is that it guarantees that it is non-empty. Okay. So, this comes from axiom of choice. Okay. So, the best way one can write this product of xi, like again depending upon which indexing set that we are using. So, one way to write down is that suppose f of I, if you denote it by xi, then you can use this tuple notation xi ini again to denote this product of xi. So, this is also one can use. So, where xi comes from capital X. So, this is exactly the product of xi. So, this notation also used many times in various books, but I would personally prefer this when you considering the infinite collection. Okay, so this is actually gives you the definition of the Cartesian product of xi for any collection I. So, implicitly I have used indexing set, okay, but what is the meaning of indexing? So, that let me make it very clear. So, here is the definition of indexing. So, you start with two non-empty sets, okay. Let us say capital lambda and capital X, both are non-empty sets. So, then I want to talk about indexing of this capital lambda, okay. So, indexing over this capital lambda. So, then what is the meaning of that? So, indexing, broadly speaking, it is just a surjective map from lambda to x, okay. And indexing or labeling a surjective map from capital lambda to, let us call it phi x. So, usually what we do, like once this indexing is fixed, we are calling it as phi. So, phi is from lambda to x. Then note that phi of alpha, so they are elements of x. Since phi of alpha is also treated as a set, so this is itself a set, okay, because elements of sets are also sets. So, now you can see that the images or the indexing that we are talking about. So, you can write phi of alpha, alpha in lambda, okay. So, this is how you label these sets phi of alpha. So, this is what called indexed family or indexing. This lambda is called indexing set, this lambda is called indexing set, and this is called indexed family or the collection of sets over lambda, okay. So, since all elements are sets in Z of axioms, so we refer this collection to be the family of sets, okay. So, in practice what you do, so in the previous case you have taken x to be the union of xi. So, now the map, the indexing map is given by, okay, where phi is given from, like say capital I to this x, where I is mapped to, okay, sorry, the x is not union xi, I want I to be xi. So, x is the power set, x is the power set of this union where I goes to xi. So, that is what we are taking. So, then you are actually indexing this union xi to be just this union of xi. INI. Okay, this is what we have used. So, in practice it is very clear that what is the meaning of indexing and how you index. So, most common indexing set is this 1 to n, which is the finite indexing set, and you can write down the first n number of positive integers as 1 to n. The most sophisticated is the matrix. If you take indexing over, let us call this is I n. So, then if you take indexing over I n cross I m, then what you get is actually matrix. You denote it by A I j, where I varies from 1 to n and j varies from 1 to m. So, this is again another way of indexing. Here we are talking about the arrays. So, we are only interested in the set. So, this is an example of set where we are using the indexing, that is again coming from I n cross I m. We can also talk about a sequence. So, that is an indexed elements which are actually coming from some given, let us say R. Okay. So, we also talk about sometimes this infinite family indexed over, let us say, natural numbers and so on. Okay. Later maybe like later part of the course we will actually see more examples of indexing and then how to index them. But indexing, so they are very important in partitioning the given set. If I start with the set X, and what I want to do, I want to divide that set into like union of smaller sets, such that in that smaller collection they are like disjoint to each other. Okay. And that is what we call it as a partition of X, and the partition of X actually kind of more important. And how the partitions comes from? The partitions will come from actually equivalence classes, and we will prove that like there is a one-to-one correspondence between partitions and equivalence classes of X. Okay, let me make the definition of partitions precise. So, here is the definition. A partition of X is a family of, let us say, subsets indexed over lambda such that, so the very first thing is X should be union of all X alpha. The second thing is, whenever you take X alpha intersection X beta, this should be empty for all alpha not equal to beta inside capital lambda. Okay. So, this is what we call it as a partition of X. So, if X looks something like this, then what you do? You just partition this to something like this. Okay. And this is what your typical X alpha, X beta and so on. So, they should not share any elements between them, and the union of that should be entire capital X. The most practical way to get partitions, you define an equivalence relation and then look at the equivalence classes, and that will form a partition. So, let us first see some examples and then later we will prove the correspondence between them. For example, what you can do? You can actually take the real line, okay, and then take the real line partitioned as follows. So, you look at geometrically. So, you have 0, 1, 2, -1 and so on here. Now, what do? You take this 0 and then exclude this 1, look at only this closed 0 comma 1. So, closed 0 comma 1. Okay. So, now what you do, you can actually just translate that, then take this closed one and then open 1 comma 2, sorry, closed one and open 2. Likewise, you can keep doing, and on the other hand, here also you can do this close minus 1 and then open 0 and so on. So, now it is clear that this clearly forms a partition of R into these intervals. Okay. So, now look at this example which is like R 2. Now, what you can do, you can actually take this x axis. Now, you can take any line that is parallel to x axis. So, this is x axis translated by some, let us say x naught comma y naught. Okay. So, this is going to be my y naught. So, now it is clear that if I take these parallel lines which are parallel to x axis, and that will form a partition. So, R 2 can be partitioned into, we usually write it as this symbol which is like rectangular shape union. You put a dot here to say that it is disjoint union, such that this is like those lines that are parallel to x axis. Okay, that will form a partition. Similarly, you can pick any line. Okay, so you can pick any line and then look at all the line which are parallel to that. That will also form a partition of R 2. So, again now let us take the punctured this complex plane, then you can see that. So, you just remove this origin and then remaining things will be there in your plane. So, now if you take this circle centered at origin, all these centric circles, they will form a partition. So, you can actually just draw like this, you can see that all of them, this will be the union of circles centered at origin. Okay. Similarly, you can also do something like this. You can take this plane without origin. So, now if you take a ray which are like starting with this 0, and then you can take possible rays like this, and that will again form a partition of this C cross 0. Okay. So, one can come up with many interesting examples, and then like if like more geometrically, like what we can do. So, we can actually take so this plane, and then what we can do, we can include this line and then exclude this line and then take only this part. So, now by rotating this, we can go to here, and the second part will be this one and then this one. Similarly, so this is the first part, this is the second part, and then similarly you define fourth part, third part and fourth part. Then 1 union 2 union 3 union 4 is going to be exactly my R 2. So, there are like many examples one can come up with like this. Okay. And if you think about it, equivalence classes or equivalence relations, so they gives a uniform way to approach this partition. Okay, so I will stop here, and maybe in the next class I will actually explain more about the connection between the partitions and the equivalence relations. I will stop here. We will explore the connection between partitions and these equivalence relations in the next class. Thank you.